Okay, so let's continue to the single cycle architecture. We're now diving into the hardware design. What we talked about earlier, the ISA. The ISA is basically the states that are visible to the programmer. What do I mean by visible to the programmer? Essentially means that programmer can interact with the ISA through assembly. I can write a program in assembly language using the ISA specification, and the computer will run, right? Sometimes states inside the ISA, for example, things like what is in a register, these are called architectural states. What are the architectural states, or what are the examples of these? They can be the name of the register, like R0, R1. In x86, it can be EAX, EBX, ECX, EDX. The program counter, or sometimes we call this the instruction pointer. Also the memory. The memory store the location of your, store your data, essentially, that are indexed by some address. And the programmer can directly see and handle these values. Then there are things that are not visible to the programmer. For example, when you write a program, can you control the cache? The answer is not. You cannot really directly control the cache, right? These are the microarchitecture states. These are things that are happening inside a computer, and these are not exposed to the programmer. There's no way for the programmer to access things like the value of the certain hash blocks or the intermediate value of your register that are in the middle of the execution are not going to be exposed to the programmer. When you run one line of assembly, when you run one single instruction, the value of the register that programmer can access should be either before you start executing or after you finish execution. So it's either before or after the instruction is done. While the action is happening, you should not see what's going on there. Now that we have the ISA, right, we have a method to actually command our computer. And the hardware now becomes things that just connect the circuits together and interpret or make sure that I can run all the command. Right? At the end of the day, I need to build the hardware to follow the ISA and the ISA's command. All right. So if you think about this, again, architectural states are the state of your computer. Basically, when I said the word state, it means the status of something. So the status of your computer as seen by the programmer, let's say you're at architecture state 1. Programmer see the computer having this status right now. After you process one instruction, after you finish one instruction, essentially what happens, you're transitioning the status of the computer from AS1 to AS2 based on the ISA specification. The command tells what AS2 will look like. For example, if the command is adding the two numbers, AS2 should show the results of your addition. All right. So now ISA specify what AS2 looks like given the instruction and original state. Now what's missing? What's missing? From the programmer point of view, right? From the programmer point of view, nothing is missing. We're done. We're done, right? From the programmer point of view, as long as I can finish one instruction and move on to the next state, it means that for any number of instruction in your code, I'll just keep consuming instruction and move from AS1 to AS2 to AS3 to AS4 to AS5 until you finish every instruction in your program and you're done. Okay, that's it, right? But in reality, the microarchitecture would implement how do you get from AS1 into AS2. It's the hardware that actually perform the action. All right. And in this step, there can be any number of intermediate steps in the middle. And there are many design choices. You can have AS1 to AS2 in one single clock cycle. Everything happened at once. This is your lab 1, basically. You can also have some intermediate steps, AS1 into some transitional steps, into another transitional step, into another transitional step through multiple clock cycle. This is basically your lab 2, right? So AS1 to AS2 in one single clock cycle, it means that I need to make sure I clock your CPU in a way that's not too fast, because if I say that, okay, can someone give me some action? So let's say I have to go get lunch, all right? Let's say I tell you, go get lunch, okay? How long does it take for you to do it? Go buy lunch, like takeaway. Okay, 15 minutes, all right? That dictates the speed of your clock. So now you have multiple people answering me, which is awesome. Keep answering. Keep answering. Anyone else having different number? Okay, let's say 5 minutes is bicycle. Okay, so if I put in the command and say, please go get lunch, right? Some of you might take 5 minutes because you have a bike. Some of you might take 20 minutes because you have to walk. Some of you might have to take 15 minutes because you're super hungry and you walk faster. In this case, let's say I need to build a clock that say when I clock in the next cycle, everyone has to basically got their lunch. So how fast can I clock this? How long should one clock cycle be in this case? What would happen if I say my clock cycle with 5 minutes? Basically, no one would have their lunch, right? It's too short. So if I assume that AS1, the architecture state 1, is when you don't have lunch, AS2 is after you got lunch, because my instruction is go get lunch, right? Go buy lunch. So in this case, how should I set the clock? How long should the clock be? Is it 5 minutes, 20 minutes, or 15 minutes to ensure that everyone got their lunch? The longest, right? Maybe 20 minutes, because if I clock too fast, people that people that need to take 20 minutes will not be back yet. They're not in AS2. They're like, I'm trying to be in AS2, and then, oh wait, too late. I am in this limbo status where I haven't even had lunch. And now what to do, right? So the trade-off that you can see obviously is if I want to go from AS1 to AS2 in one single step, it means that every one of you will have to wait 20 minutes when I said go get lunch. Okay, even though you have a bike and you got your lunch in 5 minutes, you have to wait for your friends, because that's the clock cycle, right? So that's the first trade-off. What if I say this? What if I clock and say, okay, if you have a bike, you can go there. If you have to walk, you do some checkpointing where when you're in the, like when you move 5 minutes, I clock once and you save your progress. You don't tell me that you got whether you got lunch or not. You just save your progress. You stay there, then you move to the next clock. So people that has the bike spend one clock cycle, come back and now have lunch. People that doesn't have a bike, yes, exactly. If you take a bike I do everything in one cycle, you got back in 5 minutes, you just sit there and waiting, right? Because the clock cycle hasn't proceed. You cannot really begin from AS2 into AS3 and process the next instruction until I clock. So if I do multiple clock cycle, I do temp 1, temp 2, temp 3 before I do AS2. In this case, let's say I clock at 5 minutes, right? If you got lunch with the bike, you are done. You're now in AS2, which means that if I clock faster here, I can move on to the next thing I need to do. But let's say your friend who take longer time, the 20 minutes latency, all right? It means that, well, it's okay. I'll clock 4 times and I'm also in AS2. You see how in this case, the trade-off is I am allowed to clock more often. And when I can clock more often, I can start the next action whenever I'm done. And let's say I'm done earlier, I can be faster. I can finish my work faster. All right. Is it more clear now with the example? So some quick background. You might have, if you are in the electrical engineering program or computer engineering program, you might have heard of these two things already. I just want to say, hey, if I mention this, let me know if you don't know what's going on. Combinational logic means that it's the set of hardware logic that are being put together to perform an action. In order to perform an action, sequential logic are logic that are being put together to dictate the sequence of things. This is to control the time. Why? Because the program run based on a sequence. You run the first instruction, followed by the second instruction, followed by the third instruction, followed by the fourth instruction. It happened in sequence. So you need to have the sequential logic to control the sequence that go first instruction. If you're done, then next instruction. If you're done, the next instruction. All right. And that's a clock. The clock in the computer basically kind of dictate where the transition between one action is moving to the next action. It transitions from one action into another action. Critical part is if you look at your design, which will include wire, right? And some logic gate, right? And you don't have to understand what do I draw right now. Great if you understand that these are the AND gate followed by an OR gate with 3 inputs and 1 output. But the critical part basically means that if I look at my logic, how long does it take for me to make sure the electron from here go through the wire and propagate all the way to the output? Basically, if I change the input value, when do I see the result? The critical part is the part that takes the longest time. Why is this important? Because this dictates how fast can I clock. The critical part, I need to make sure before I clock to the next action, I need to make sure the electrons get all the way from the input to the output. All right, so the critical part dictates how fast can I clock. In a single cycle processor, what we need to assume right now, this is the simplest form of processor design. I want to compute everything in one cycle. Again, the design is I want to get from AS1 to AS2 in one cycle. And that's it, right? Why is it simple? Well, everything happened at once. No intermediate steps. So AS1 would first go to combinational logic to make sure I have the result. Then you got to the AS2. Then the AS2 will go through the sequential logic to save the state and repeat. All right. Now, what is going to determine the critical part of our combinational logic is if you look at all instruction in the ISA, the slowest guy instruction. Why? All right. So my answer to this question is it's going to be the slowest instruction in the ISA. So why is this the case? First of all, what I just said is if I want to do single cycle processor, every single command will take 1 cycle. All right. In your processor, also, you need to support every single command, which also means that for every single command, I need to make sure my clock is slow enough, again, slow enough that the slowest guy, the slowest command can finish the task. All right, is it more clear now? Why is the slowest instruction is going to dictate the critical path? Because that would determine how fast can I clock. I cannot clock any faster than this, because if I clock faster than this, I cannot support that instruction. Any question so far? มีคำถามไหมครับ? So let me pause here for a bit and just make sure is there any questions here. Okay, I get one emoticon saying thumbs up, so I think we're good, right? Now, again, slowest instruction determine the clock. So what if my instruction want to access the memory? That's gonna take a long time, right? Or if it's an IO, that's even longer, right? You probably do not want a 1 kilohertz processor, right? Because if you build a single cycle processor, it's gonna be 1 kilohertz or worse, right? It might be like 1 hertz processor. 1 clock is 1 second, right? I mean, it's probably not that bad, but still, it's gonna be bad, right? I mean, look at processor nowadays. You're looking at gigahertz processor, so this 1 million times worse, right? But here's the thing, because this is the simplest design, so let's first study how we can build this. Then we optimize it to make it faster, all right? Now, another question I want to kind of make sure that's in the back of your mind is when you run a program, how do you measure the performance, not of the program, but of your hardware? How good is your hardware? All right. So what needs to happen in one single cycle? Basically, instructions are processed in steps, right? So recall from the first lecture, instructions are in the memory. When we run a program, right, the OS put the binary into the memory, and then you first point to the first line of your code and say, run that instruction. So the first step is I need to go and fetch the instruction. The first thing I need to do is, well, now I know where is the first line. I need to go there and get that instruction. We call this fetch. After we have the instruction with me, the next step is to figure out what am I supposed to do with this instruction? Is this an add? Is this a multiply? So we call this decode. Decode means trying to figure out what's my action. Then if you finish decoding, the next thing is you need to check if there's any address involved. Do I need to get any more data for your adding or subtraction or your multiplication? Or if you need to get any operand, any input for your instruction, right? But now you know you have to do an add. Addition takes 2 inputs, the left input and the right input. Where is the left input and where is the right input? Go and fetch the input data. Then you execute. Execute means perform the action. Afterward, when you execute, you need to then make sure you put the results back because you finish an add The result of an add need to be stored back either in the register or in the memory. So that's the steps, right? Fetch, decode, execute, and write back. Store the result back. Okay. Quick note that not every instruction required all the steps. For example, some instruction doesn't need an address, so you go and fetch, decode, then you execute right away. Get the operand and execute right away, right? Now, before I go into the deep dive on the design, not even deep dives, we're like going high level on the design. The next thing you might have right now in terms of the question, right? Because I just told you an alternative design where instead of one really long clock, why can't I clock a bunch of time and then save progress? Like the going get lunch example, if you have a bike, then you can do the whole thing in 5 minutes. If you do not have the bike, then 20 minutes is fine for clock cycle, right? We call that multi-cycle processor. And the difference again is single cycle processor, everything is done in one clock cycle. Multi-cycle processor, it means that the steps are done across multiple clock cycle. It means that every time you clock, you just need to make sure you save your progress, right? You save your progress, and then you move on from there. An analogy of this is, how many people ever play the game called Rockman? Am I too old? มีใครเคยเล่นเกม Rockman ป่ะ? So the game, which by the way is quite fun, right? I did play that a lot. Yeah, that. I did play that a lot when I was middle school, right? Long time ago. One other thing about this game is you need to finish the whole stage before you can save any game, right? If you play that game, you need to go and fight and meet the boss, fight the boss, and kill the boss before you can save your progress. What happened if you die in the middle? You rerun from the start, right? So imagine that as a single cycle processor, you need to finish the entire thing, the entire stage, right? Before you can move on to the next action. Multi-cycle processor is where you have checkpoint in the state where you go and like, let's say you start from here, right? The boss is here. The boss room is here. You basically keep playing, and then there's a save point here. If you happen to fall down or die in the middle here, instead of starting all the way back, you start here. Then you keep going, then you kind of have another checkpoint before you fight the boss, right? So think of that as like multi-cycle processor. When you want to fight the boss, like one action, it can be done in multiple clock cycle. You save the checkpoint, right? It is not like you fail and rerun, right? But I just want to show you the analogy that multi-cycle processor, the same thing. Go and fight the boss, but now you happen to do in stages. Each of the steps can take many cycles to complete, right? Think of add and multiply. How many people spend a longer time to multiply two number comparing to adding two number? Which one is longer? I mean, addition is going to be quicker, right? Obviously. So one thing I can do is I'll just make a really fast clock and say adding take 2 cycles and multiply would take 4 cycles. I mean, I can do that, right? So that's a multi-cycle processor design. Our modern computers are built as a variant that are much better than the multi-cycle processor, but it's built this way, okay? The next piece of background before we kind of dive deeper is Datapod versus control logic. When you process an instruction, right, you move from architectural state 1 into architectural state 2. from the data point of view, basically you're transforming your data from D1 to D1 prime. Think of it as a math function, right? The function unit process your data, spits out the output. The instruction tells you what the operation is, and the process instruction consists of two components. The data part, which is the hardware that deals with transforming D1 to D1 prime, which is the functional units or the actual structure that move the data around or the storage. And also the control logic, which are the hardware signals that control the data part. All right. In this case, the select wires will go into the mux and kind of trying to figure out, okay, how do I take the input? Where's the input coming from? So that's the control logic. Again, the difference. Data part is the hardware that involve changing your data into D1 prime. Control logic is a hardware that involves how do I make sure it's a controller that makes sure D1 move to D1 prime. So now let's say we have a toy example. One typo here. I should call this the program counter, not the instruction register. Give me a second. So I have the program counter. Program counter points at the line you are running right now. All right, it points to the line that you're running right now. So what you do is, because I point to the line I'm running right now, the address, we use this as an address saying, hey, go get that line, because that's where we are. That's the line in the program you're running, right? Then once you have the instruction, the instructions then put to the decoder. The decoder then break down the instruction and try to figure out, okay, what do I supposed to do here? Is it an add or is it a multiply? Now, let's say it's figure out, let's say it's an add instruction, right? Add instruction involves two inputs. Again, an add involves two inputs, the left and the right side of your add addition. So in that case, I would just select the left input and select the right input, put that into my adder. I put that into my adder. If I need to save the result in the memory, I can have another wire that connects to the memory and say, hey, the result goes there. Or sometimes the result is being overwritten into another register. Basically, R0 plus R1, that's the action. Then you write the results into R2. So these go into the register file. And again, the decoder has a select wire that pick out where is the input data to the register file, and also which register are we updating. And now that we are done, right, the last thing is update the program counter to move to the next line. Again, the key here is point to the first line that you run, decode what the instruction is, gather everything you need from the hardware, put that to the functional units that you want to do, in this case, an add. Then you finish the action, write the result back, and move program counter to the next instruction. Okay, so let's start with from our toy example. Let's start with some simple toy ISA that has 3 register file. This means that I have 3 bits for each register, because if I have register file from R0 to R7, so that's 8 of them, I can use the bit 000 to represent R0, 001 to represent R1, and 111 in this case would represent R7. Every time I want to figure out what register are we talking about, I look at the 3-bit pattern and see, oh, is it 101? It means R5, because R101 is 5. If it's 100, it means 4, R4, right? And let's assume 3 address machine. We have source 1, source 2, and destination. This also means that if I have an add operation, it's going to involve 9 more bits because I need to specify source 1, source 2, and destination. Now, what do we need? Again, instruction involve, first of all, the opcode, right? And then the setup bit that represent source 1, source 2, and destination. Then if you need to deal with constant value, we call this the immediate bit. Basically, it's just the bit to say, whatever goes in there, treat that as a constant value. And now let's remember again that we are defining our own ISA. We can do whatever we want as long as we can decode this. Okay, so let's say here's our toy ISA. If it's a compute instruction, I would make sure bit 9 to bit 15 represent the opcode. It can be an add, a subtract, or multiply. And bit 6 to 8 is source 1, 3 to 5 source 2, 0 to 2 is destination. This is kind of like a poorly drawn, poorly designed, really quick toy ISA, by the way, because you can see source 1 is not aligned, source 2 is not aligned. It's just whatever, right? I just want to quickly like have a table that's simple to draw. So let's say the opcode for an add is 0000011. Whenever I see this bit pattern in my opcode 0000011 is an add, right? And let's say I can pick whatever other opcode for the load immediate or like a branch or whatever, depending on my own choice. I can design this. Now, let me ask you one quick question. In this case, how do I do add? Which basically means I want to do R1 plus R2 and then write the result into R0. How do I represent this instruction in binary? We know that the opcode for an add is 0000011. It means that the bit 15 to bit 9 is going to be what? Is an add, right? So it's going to be 0000011. What is source 1 here? Source 1 is going to be the left side of the add, right? So this is source 1. This is source 2. And this is destination, right? So source 1 is R1. And what I said in the earlier slide is I said, hey, let's assume R1 is 001. So I would specify R1 as 001, R2 as 010, and destination as 000, because this is going to be R0. This is R1. That's R2, my bad. So that's R2, and this is R1, and this is add, right? So whenever you fetch and you see this bit pattern, you now know that's okay, that's add R1, R2, R0. Any questions so far? Basically, that's gonna literally be what is in the memory when you fetch that bit 000001100100000. And when you read those bits, you know that from the ISA specification, you know that okay, that's just adding R1 and R2 together, write the result back to R0. All right. Sorry, this is the same example. All right, add R0, R1, R2. So the same example again. Is going to be 0000011 001 and then 000, because this is R0, this is R2, this is R1, and this is the add. Okay. Now, let's map this back to our toy example again. Sorry about this. This is a program counter. Okay. So let's say the program counter point to that add 0, R1, R2, right? Over here, when you have the address pointing to the memory, you're gonna see again that bit, exact bit pattern. And you get the whole thing here, right? This whole thing is actually, to be honest, there's like another register called the instruction pointer register. This thing store the instruction. And this thing is feeding to the decoder saying, hey, here's my bit pattern. Decode this. Decoder knows it's an add, right? Decoder now knows it's an add. What are the source 1 and source 2 of my add? That's going to be R1 and R2. So in this case, the decoder fetch R1 and also fetch R2 to my adder. Then once you're done, the adder will forward the data over here. This would then select R0, put the result of R1 plus R2 into the register file, and overwrite whatever is R0. So now R0 should now have R1 plus R2. Then the next step is update the program counter so that you move to the next line. So from program counter, which is address, the next line is going to be address. So let's say instruction is 16 bits long, right? That we had earlier. So it's going to be address plus 2. So again, sorry about this. It should be plus 2 because our instruction, we assume it's going to be 2 bytes long, 16 bits. All right. Now, when you do address plus 2, it instead of pointing to this line, now it points to the next line. Then the same cycle happen until you finish your program. All right. We can also extend this to do a load. A load is just, I mean, to be honest, it's like the exact same thing that happened, right? You figure out here, this is your instruction. All right. Instruction is put to the decoder. It's like, oh, okay, it's a load. What does a load do? The load means that I do not want any operand and except the address. So you basically take the address from either the immediate or the operand. You feed the address you want to load. So this is going to be the address you want to load, right? When you do that, the memory, the output is going to be the data correspond to the address from the loading address, which is now forward here, right, into the register file, because that's the target of your load. You want to load something from your memory into the register. So in this case, the decoder will know and make sure that it writes to that register. Then you move the program counter PC plus 2. Again, this is again PC, not IR. So now address will become address plus 2, which move us to the next instruction. What about branches like if else, right? If else doesn't really do much here except for maybe check the condition or like check if this is true or not. But instead of doing PC plus 2, which is moving to the next line, we would then make sure decoder will select any of these inputs depending on where we are jumping to. Basically, when you have a branch in your code, like an if else, right? The next line might be the line right after the if. But then somehow you don't always go to the if, right? Somehow if you go to the else part, you need to make sure the program counter jumped there. So that's it. Basically, for branch, you just need to make sure you update the program counter with that next line that you have to run. All right, now let's go back and revisit the concept I mentioned earlier, which is multi-cycle processor, right? Because in the single cycle processor, everything happened in one cycle, which means that all the control signal are going to be generated in the same cycle, and the transformation from D1 to D1 prime happen in the next cycle. Multi-cycle processor, the control signal will just be the one for this particular steps. For this particular cycle, this particular steps. So this allows you to decouple the latency of the control signal from the hardware Datapod, the Datapod that dictate when you do an add, right? We'll go into more detail later in the third part of this lecture when we talk about pipelining. So now let's double check the slides a little bit here. where we are. Okay, I think we're good. So let's do a quick break here, and we'll come back at 11 o'clock, and then we'll continue with pipelining. All right. So afterward, we can come back and talk about multi-cycle architecture, followed by pipelining. And most of the focus will be on pipelining and how do we make the CPU faster. All right. So let me stop recording so we can break the video down into 3 chunks, and